I am Marco Gavicini from the University of Pisa, Centro Piaggio, and I will be chairing this session. This session is a long talk, and is given by Raphael Deimel, and his work is from the Technical University of Berlin, and his work is a novel type of compliant underactuated robotic hand for dexterous grasping. So please, Raphael.
So hello, everybody. Thanks for showing up. And the presentation is going to be about this hand, as it shows. Up. So now it's working. So the presentation is going to be about this hand. As you can see, it looks and it also works very differently to most hands you probably have seen before. This is because it is made almost entirely out of soft rubber. It is inflated, and this actuates the hand. And because it is made out of soft rubber, it is very compliant and can adapt to the shape of objects. It is also soft enough to not damage delicate objects like fruits and vegetables, as you can see. I want to tell you in this talk about how we built this hand, what its capabilities are, but I also want to tell you why we built this hand. And for this, I have to take a step back and talk first about human grasping. It turns out that if you take a look at how humans grasp, that there's a lot of interaction going on between the hand, the environment, and the object. And to illustrate this to you, I want to show you two examples. The first one is of a human grasping a plate from a table. And this happens very fast, so we're going to look at it in slow motion. What you can see here is that actually the fingers do not touch the object first, but the table. Then there's a sliding motion of the thumb, which actually creates the contacts with the object. And then there's another motion where the fingertips roll, and also the plate is rotated around the pivot created by the thumb and the table. And only then we actually achieve the proper grasp. So what you just saw here were three interactions which enable a human to tolerate some of the uncertainty which is present in this situation. For example, the height of the object and also the placement. Now, to show you this is a very simple example, and to show you that this is also happening in more complex manipulations, I want to show you an expert manipulator. And this is Julia Child. Some of you might know her. She was a TV cook in the 60s, and I'm going to show you a video, a short sequence of 6 seconds of one of her shows. I want to thank Matt Mason here for pointing us out to this video, because he made us watch it literally hundreds of times. And this short sequence is from the Potato Show, and she's cutting potatoes. And you can see here, she's manipulating lots of things, and it's very fast. But ultimately, anybody of us could do this. Maybe you need a little practice, but it's nothing very special. Now, we put on our interaction goggles and went through the video and annotated each of the interactions we saw, which simplifies and helps to achieve robust and reliable manipulation. And what we found was an astonishing amount of interactions happening. I cannot go into detail through all of them, but for example here, the blade was positioned against the knuckles to position it precisely. You can also see, for example here, the potato is flipped over the edge created by the table and the potato. Potatoes are slid around the surface, they're flipped over, and so on and so on. If you count all those interactions, just in 6 short seconds, you count more than 30 of them. So, wouldn't it be nice if robots could do this too? And this is exactly what we want to do. We want to transfer this principle to robots and make them grasp using those interactions. Now, if we want to do this, we also need a hand that facilitates those interactions, that make it easy to implement them. And this is exactly the goal of the soft hand. It is to facilitate the compliant contact, to maintain the contact, but also to simplify the control of those interactions, of those what you just saw. But we don't want to achieve this by trading off the dexterity of the hand. So we want to have a hand that has a diverse set of graphs, can do a diverse set of interactions. We do this by maximizing the compliance of the hand and also maximizing the degrees of freedom, because both help you in implementing different interactions and also to have a diverse set of interactions. It also helps to make the hand robust, because we're going to operate close to surfaces and other objects. Errors are going to happen, and so we're also going to have unexpected collisions. So now that you know what the ideas were behind the hand and why we built it and what the goals are, I can talk about the hand design and the components of the hand. There are three main parts. The most important one are the so-called NuFlex actuators, and which you can see here. Each finger is one actuator. There's a slightly bigger one here, which is the thumb, and there's also two more here in the palm. The actuators are arranged using a scaffold, which you can see here in the side view. And as a third component, there is a palmar pad, which you can see here in the side view and also here in the front, which not only covers the gap between the fingers and the palm, but it also stabilizes the structure and helps us with grasping. As I said, the actuators are the most important part, so I'm going to show you them in greater detail. And for this, I cut up one of the fingers for you. And here's the view of those. On the top, you see the outside of the actuator, up here. And on the bottom, you see the inside. The actuators are pretty much built like a balloon. They're made out of silicone rubber. And there's a small air supply tube where we can use it to inflate or deflate the actuator. Additionally, there are some fibers reinforcing the structure of the actuator. The most prominent one is here, the red thread bound around the actuator in a helical fashion, and this restricts it from expanding radially. A second fabric is embedded here in the bottom layer. It's less obvious. You can see the letters here, they're actually printed on this fabric. And this fabric restricts the rubber from expanding on the bottom side, from extending there. And the only motion that the rubber can do is expanding here on the top side along the actuator. And when we inflate the structure, what happens is that the finger bends. So here you can see the finger being inflated and deflated periodically. It doesn't change a lot in radial size, but it has a strong bending motion. And this is the basic of the NuFlex actuator. The second important part of the hand is the palm design, because for an anthropomorphic hand, we need an opposable thumb. And for this, we designed NuFlex actuators that are curved. So you can see here two of them, colored in red. And both of them make up the palm of the hand. The palm is actually mounted here on the top side, and the thumb is here connected to the palm. And the motion that is created by those actuators you can see here in this movie, this is basically the opposition of the thumb you see. And then there's also the thumb being inflated so you can see how it moves. Because we have two actuators, we can also inflate them differentially. And this creates a motion of the thumb within the hand. And we're going to come to that back later. It's going to be very important. But before, I also have to talk about the actuation of the hand. It is pneumatics, so we have to inflate it. And one of the nice features of pneumatics is that you can easily under-actuate and inflate several actuators at the same time with the same control channel. And this is also what we did with this hand to simplify the control. The letters here denote the control channels we used. So we inflate the small, the ring, and the middle finger together, as we do with the thumb and the smaller one of the palm actuators. This reduces the number of degrees of freedom we have to actuate from 7 to 4. And this is the setup we also used for the experiments later. But now I want to come back to the palm design. I said it's very important to have a dexterous thumb because this is considered a prerequisite for a dexterous hand. And to check this, in the evaluation, we recruited a test from medicine, which is called the Kapanji test. And this one is used for assessing, for example, the thumb dexterity after hand surgery, whether it's a functional thumb or not. The test is very simple. There's 8 points on your hand, which are shown here with these white dots. And you have to touch them with the tip of your thumb. And you just count the number of points, and the more points you get, the higher your score, and the better your thumb dexterity is. So how does a hand fare in this test? Well, number one, doesn't work. But we can touch the middle of the index finger, we can touch the fingertips, and we can also touch the middle and the base of the small finger. So this gives us a score of 7 out of 8 points, and this is very good. If this was the score of a hand surgery, this would have been considered successful. Now that we know we have a dexterous thumb, we can ask ourselves, do we also have a dexterous hand? And hand researchers usually show this by implementing a diverse set of grasps, and usually they also rely on using a grasp taxonomy to select those grasps so that they are very diverse. We took the same road and used the so-called Fikes taxonomy for this, which is the most diverse one we know of, which contains 33 different grasps. I'm going to show you some examples of the diversity of those grasps we could achieve. So the first one is very simple. It's a power grasp for cylindrical objects. You can also do a power grasp for spherical objects. But there's also, for example, precision grasps, like grasping with a fingertip. The taxonomy also implements, has some intermediate grasps like those, and some more specialized to specific purposes, like, for example, holding a pen for writing. Overall, we managed to implement almost all of those grasps, and we were very surprised, and especially because this is the first prototype we built, so we weren't expecting it to work this well. To be complete, 2 grasps we couldn't replicate. This is the one on the left is holding a very thin stick in your hand, and the right one is, as you can see, grasping scissors. Nevertheless, most of the grasps we could replicate, and I also want to point out, again, we could replicate this with only 4 degrees of freedom. So this means that we could replicate all those grasps with just a few number of input channels. Now we could ask ourselves whether maybe the grasp postures here are just very low dimensional. And to check this, we recorded the grasp postures for the Fikes grasps and estimated the postural, the dimensionality of the posture space. We used a principal component analysis for that, which is quite common in hand research. You already saw today in the morning in one talk the synergies, which are basically just the principal components of the grasp posture. What you see here in this graph is that the residual variance of the principal components given for a certain number of components that are left unaccounted for in your data. So if we want to explain the whole postures, we have to go out to like 8 to 10 dimensions to fully explain the data. So this gives us an indication that the posture space is about that size. So the question now is, where does this come from? We have a 4 degrees of freedom actuation, but there's an 8-dimensional behavior observed. And our explanation for this is that the hand and the object interact with each other. The hand is compliant, so it can adapt to the object, and this differentiates the grasp from the 4-dimensional grasp, from 4-dimensional actuation to the higher dimensional grasp posture. So to conclude my talk, I showed you a compliant underactuated hand, which is actuated pneumatically. I showed you a novel palm design using continuum actuators to create an opposable thumb. I showed you many different graphs that the hand is able to do, and in fact, we can implement most of those graphs of a very comprehensive graph taxonomy. But what I didn't show you yet was what I was talking about in the beginning. We want to use this hand for implementing grasping strategies that use interaction with the environment, that exploit constraints to motion in the environment. And so one of the things the hand has to do is to make these interactions easy for robots. We're not there yet, but I can show you the first videos of our trials. Here you have the hand, and it's trying to grab the snack bar out of the bowl by first sliding along on the bowl, on the floor of the bowl, and then reorienting and grasping against the bowl. And here you can see again the video from the beginning, and you can try to spot the interactions that the humans are using it here. And to show you also that the graphs of the taxonomy also work on the table, here there's some images or some videos showing you how to use those graphs in a real setting. Okay, that's it. I hope I showed you an interesting way of grasping. It's very different to what you normally see for robots grasping. And I hope I could inspire you with this talk. Thank you.
Before the questions, I would like to recall that this paper is an award candidate.
So I wonder whether, it's a really impressive hand. I wonder whether you thought about how you position the manipulator that carries the hand in order to start the manipulation in a way that's conducive to doing compliant grasping. So part of the trick to do this, of course, is to have the right orientation when you approach, and then initiate and trigger, and then you sort of get this compliant grasp. So I wonder if you have any thoughts on how manipulation strategies would be impacted for this new kind of end effector that you're having.
Yeah, so that's true. A very important part, which is often overlooked, is actually the wrist motion and the end effector motion directions. What we're trying to build here are kind of motion primitives or motion sequences we can use. For example, going to a surface, for example, perpendicular to it, to approach it from that way. Of course, we're going to have some perception, so we know roughly where things are. We don't know exactly where they are, but roughly. And we can use this to avoid, for example, certain situations. What you saw in this video in the beginning is also that we can handle some collisions and some uncertainties, which help a lot in this regard for moving the wrist. That's very helpful because you don't need so much precision. Actually, this grasp here is just joint control, so there's no upspace control, for example.
So scoring 7 is actually great. That's what we know. But the question is, like, is it impossible to go for 8, or is it? Or why didn't you go for 8?
So we didn't go for 8, or well, we tried to go for 8, but this is the first prototype. So we were designing the hand. There's a lot of parameters we can test. We chose some just in a very haphazard fashion, just try it out. So there's obviously room for improvement. I think it is possible, but it is also maybe not exactly necessary. So we want the hands to implement a lot of different interactions, not only the grasp postures, but we also have to attain those grasps. So we have to also trade off or handle this. Maybe attaining the 8th point on the Kappanji test is not exactly necessary for still having a very useful hand.
Another question there?
Yeah, my question is can you measure the air pressure in the line? And have you thought about, if you can, have you thought about using that for contact sensing?
Actually, it's one of the first things we tried out, and yes, it works. So you get some signals back. The most difficult part here is actually if you just have the pressure sensors on the line, on the control line, that it's far apart from the actuator, and also when you're actuating, you cannot sense anything. So that's difficult here to use it in a setting where you're actually doing something. But if the hand is passive, it's a perfectly fine fine sensor strategy.
So if the last 3 fingers are activated jointly, why did you choose to make those into 3 separate digits rather than just a single digit or 2 digits?
So for one, it helps to disconnect those fingers because they can then independently comply to the object shape, so they're not coupled to each other, and can better adapt to the shape of the object. That's the most direct explanation.
Thank you.
We have another question there.
Hi. It seems ironic that this is an anthropomorphic hand that grasps well, in part because it uses the thumb in a non-anthropomorphic way. Can you comment on that?
I maybe have to tell the other people what you mean with that. It's written in the paper. Actually, the way we use the thumb is a little bit different to how humans use it. So humans use it usually on this side, and we use it like on the other side. The main reason for that is simply because we use continuum actuators, and it's much more difficult to build the actuator in a way that it actually bends to the other side too. So have like an S-shaped curve like the human thumb does. So we opted for this hand design to basically switch around and use the backside of the thumb. For our hands, it doesn't make any difference because both sides have the same properties, surface properties. Of course, that's a deviation from hand design, but it seemed to be quite successful, I have to say. So it's a detail where we deviate from the anthropomorphic hand due to different actuation technology.
How much gripping strength does the hand have? Like how much weight can it hold? Or like if you're using a bar and hitting it on something, like how hard could it hit it? I don't know.
So with this hand you saw, we can regularly hold and manipulate objects about up to ½ kilogram of size. That's kind of like the range of the hand we have here. But you can easily make it stronger if you like to. So we use very soft rubbers. You could use much higher pressures. So the hand is operated around 50 to 100 kilopascal, which is about 7 to 15 psi. You could go to much higher pressures, which also gives you much more force. Of course, there's a trade-off because if you make a stronger hand, it also has less adaptability to objects and has a stronger grasp. So what you actually want to have is some variable stiffness actuation.
Another question there?
So you showed that you can already touch, for example, different fingers with the thumb and things like that. Do you already have controllers that let you just do that automatically, where you just give it kind of a target configuration and you know how to set the air pressure?
Yeah, thank you. Until now, we used open loop control, so we just set the valve opening times for inflating. There's a small forward model for predicting the pressure we want to have and then just opens up the valve for this. Of course, in the future, it's definitely interesting to, for example, have control over the pressures, over the mass flow, for example, because this gives you much more information about where the hand and how the configuration of the hand is. But that's an ongoing research issue. The nice thing is you don't really need it for simple grasps because the hand is compliant. If you're off by a few kilopascal or such, it doesn't make a lot of difference. So you have a lot of robustness and resilience built into for this imprecise control we currently have.
Okay, so we are running out of time. So let's thank again our speaker.
Thank you.